In Chapter 7, we will cover estimating parameters and determining sample sizes. In this section, we'll begin with estimating population proportions. This section presents methods for using a sample proportion to make an inference about the value of the corresponding population proportion. Here are three main concepts included in this section. Point estimate. The sample proportion p hat is the best point estimate of the population proportion p. Confidence interval. We can use a sample proportion to construct a confidence interval estimate of the true value of a population proportion. And finally, sample size. We should know how to find the sample size necessary to estimate a population proportion. A point estimate is a single value used to estimate a population parameter. The sample proportion p hat is the best point estimate of the population proportion p. We use p hat as the point estimate of p because it is unbiased and it is the most consistent of the estimators that could be used. An unbiased estimator is a statistic that targets the value of the corresponding population parameter in the sense that the sampling distribution of the statistic has a mean that is equal to the corresponding population parameter. The statistic p hat targets the population proportion p. Let's consider this example. A Gallup poll was taken in which 1,487 adults were surveyed, and 43% of them said they had a Facebook page. Based on that result, let's find the best point estimate of the proportion of all adults who have a Facebook page. Because the sample proportion is the best point estimate of the population proportion, we conclude that the best point estimate of p is 0.43. If using the sample results to estimate the percentage of all adults who have a Facebook page, the best point estimate is 43%. A confidence interval or interval estimate is a range or an interval of values used to estimate the true value of a population parameter. A confidence interval is sometimes abbreviated as CI. Confidence levels are expressed as percentages. For example, a 95% confidence level. It means that should you repeat an experiment or a survey over and over again, 95% of the time your results will match the results you get from the population. The confidence level is the probability 1 minus alpha that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. The confidence level is also called the degree of confidence or the confidence coefficient. A 0% confidence level means you have no faith at all that if you repeated the survey you would get the same results. A 100% confidence level means that there is no doubt at all that if you repeated the survey you would get the same results. This table shows the relationship between the confidence level and the corresponding value of alpha. The confidence level of 95% is the value most frequently used. It's important that we are careful to interpret confidence intervals correctly. There is a correct interpretation and many different and creative incorrect interpretations of the confidence interval. 0.405 less than p is less than 0.455. The correct interpretation of this is that we are 95% confident that the interval from 0.405 to 0.455 actually does contain the true value of the population proportion p. A wrong interpretation is that there is a 95% chance that the true value of p will fall between 0.405 and 0.455. Another wrong interpretation of this interval is that 95% of proportions will fall between 0.405 and 0.455. A confidence level of 95% tells us that the process we are using should, in the long run, result in confidence interval limits that contain the true population proportion 95% of the time. Let's consider this graph of the confidence interval from 20 different samples. 19 of the intervals contain the proportion 0.5, and one interval does not contain that proportion of 0.5. A critical value is the number on the borderline separating sample statistics that are significantly high or significantly low from those that are not significant. The number z of alpha over 2 is the critical value that is a z-score with the property that it is at the border that separates an area of alpha divided by 2. In the right tail of the standard normal distribution. Let's find the critical value of z to the alpha over 2 corresponding to a 95% confidence level. A 95% confidence level corresponds to alpha equal to 0.05, so that alpha divided by 2 equals to 0.025. The figure below shows that the area in each of the green shaded tails is equal to alpha over 2 is equal to 0.025. We find z to the alpha over 2 equals to 1.96 by noting that the cumulative area to its left must be 1 minus 0.025 or 0.975. We can use technology or refer to table A2 to find that the cumulative area to the left of 0.9750 corresponds to the z value of 1.96. For a 95% confidence level, the critical value is therefore z to the alpha over 2 is equal to 1.96. Note that when we're finding the critical z-score for a 95% confidence level, we use the cumulative left area of 0.9750 and not 0.95. This is because we're interested in the middle area of our z distribution. And so we have to take into account the area to the far left of the graph that will not be included in our confidence interval. The previous example showed that a 95% confidence level results in a critical value of z to the alpha over 2 equal to 1.96. This is also the most commonly used critical value, and it is listed with two other common values in this table below. We can have a 90% confidence level where alpha is equal to 0.1 and our critical value would be 1.645, or a 95% confidence level where alpha equals to 0.05 with a critical value of 1.96. Or another commonly used confidence level is a 99% confidence level, where alpha equals to 0.01 and the critical value is equal to 2.575. When data from a simple random sample are used to estimate a population proportion P, the difference between the sample proportion P hat and the population proportion P is an error. The maximum likely amount of that error is the margin of error, denoted by E. There is a probability of 1 minus alpha that the difference between P hat and P is the margin of error E or less. The margin of error E is also called the maximum error of the estimate and can be found by multiplying the critical value and the estimated standard deviation of the sample proportion. The formula for the margin of error for proportions is the expected value E is equal to z of alpha over 2 multiplied by the square root of P hat times Q hat divided by n, where z to the alpha over 2 is the critical value, and the square root of p hat times q hat over n is the estimated standard error of the sample proportion. Recall that n is the sample size, p hat is the proportion of successes, and q hat is the proportion of failures. The key elements of a confidence interval are as follows. First, the objective is to construct a confidence interval to estimate a population proportion P. Second, the notation that we use are as follows. P equals to the population proportion, P hat equals the sample proportion, N is the number of sample values, capital E is the margin of error, and z to the alpha over 2 is the critical value. The z-score is separating an area of alpha over 2 in the right tail of the standard normal distribution. And finally, the requirements for using confidence intervals for estimating a population proportion P are: the sample is a simple random sample. The conditions for binomial distributions are satisfied. That is to say, there is a fixed number of trials, the trials are independent, and there are 2 categories of outcomes, and the probabilities remain constant for each trial. And finally, there are at least 5 successes and at least 5 failures in your trials. Confidence interval for estimating a population proportion P is as follows. The sample proportion P hat minus the margin of error is less than the population proportion P is less than the sample proportion P hat plus the margin of error E. The confidence interval can also be expressed in the following formats. It can be P hat plus or minus the standard, plus or minus the margin of error, or it could be P hat minus the margin of error, comma, P hat plus the margin of error. The rounding rule to round the confidence interval limits for P is to round them to 3 significant digits. Now let's review the steps for constructing a confidence interval for P. First, we verify that the requirements in the preceding slides are all satisfied. Second, we use technology or table A2 to find the critical value z to the alpha over 2 that corresponds to the desired confidence level. And third, we evaluate the margin of error such that the margin of error equals to the critical value multiplied by the sample standard deviation. Fourth, using the value of the calculated margin of error E and the value of the sample proportion P hat, we can find the values of the confidence interval limits as the sample proportion P hat minus the margin of error and the sample proportion P hat plus the margin of error. We can substitute those values in the general format of the confidence intervals. And finally, we round the results of the confidence interval limits to 3 significant digits. Let's consider this example. We noted that a Gallup poll of 1,487 adults showed that 43% of the respondents have a Facebook page. The sample results are n equals to 1,487 and p hat equals to 0.43. Let's find the margin of error E that corresponds to a 95% confidence level. Let's also find the 95% interval estimates of the population proportion P. And finally, based on these results, can we safely conclude that fewer than 50% of adults have a Facebook page? Assuming that you are a newspaper reporter, write a brief statement that accurately describes the results of this study and include all of the relevant information. Let's start with our requirement check. First, it was noted that the sample is a simple random sample. So the polling methods used by the Gallup organization result in samples that can be considered to be a simple random sample. Second, that the conditions for the binomial distribution are satisfied. Well, the conditions for the binomial experiment are satisfied because there is a fixed number of trials, 1,487. The trials are independent because the responses from one person should not affect the probability of the response from another person. And there are two categories for the outcomes, for possible outcomes. The subject either has a Facebook page or the subject does not have a Facebook page. And the probability remains constant because the probability of having a Facebook page is fixed for any given point in time. Now 3, there are at least 5 successes and at least 5 failures. Within 43% of the respondents having a Facebook page, the number of Facebook pages is 639, or 43% of 1,487. If 639 of the 1,487 subjects have Facebook pages, the other 848 do not have Facebook pages. So the number of successes is 639 and the number of failures is 848, and both are much larger than 5. The confidence interval and margin of error can easily be found using technology. First, we'll start with an example of using the StatDisk. From the StatDisk display on this slide, we can see that the required entries on the left and the results displayed are on the right. Like most technologies, StatDisk requires a value from the number of successes, so we simply find 43% of 1,487 and round that result of 639.41 to the whole number of 639. The results show that the margin of error E is equal to 0.025 when rounded, and the confidence interval is 0.405, is less than the population proportion P, is less than the population, or is less than 0.455 when rounded. Here I've displayed the formulas you'll need if you're using the technology of Microsoft Excel to calculate your confidence intervals. You can see that the highlighted rows, the yellow highlighted rows, are the rows where you will have to use a formula or do some sort of calculation to calculate our confidence intervals. In row 3, we have the number of successes, and that would be calculated based on the information we have. We have the sample size in row 4. We have our sample proportion p hat in row 5. We have our q hat, which is calculated simply by subtracting from 1 the value of p hat. And we want a confidence level of 0.95. And we know for 0.95 our critical value is 1.96. And so we have a formula to calculate our margin of error. And finally, you can see the formulas needed to calculate the lower bound and the upper bound of our confidence interval. And you can see here at the bottom, I've circled where Excel calculated the lower bound and the upper bound of our confidence interval. And I've displayed our confidence interval below the Excel spreadsheet. So our confidence interval would be 0.405 is less than our population proportion is less than 0.455. And finally, we'll calculate our confidence interval manually. I encourage you to attempt to manually calculate a couple of confidence intervals in your homework, because I think when you manually calculate these statistics, or in this case these confidence intervals, it gives you a better understanding of exactly what it is that your calculation represents. So let's get started on the manual confidence interval. First, the margin of error is found by using the formula E equals to Z of alpha over 2 times the standard deviation of P hat times Q hat over N, where Z of alpha over 2 is our critical value. In this case, it's 1.96. P hat is our sample proportion of 0.43. Q hat is a sample proportion of failures of 0.57, and N is our sample size of 1.87. And so our margin of error, E, is equal to 1.96 multiplied by the square root of 0.43 times 0.57 over 1,487, and that is equal to 0.0251363. And now we can construct our confidence interval. Constructing the confidence interval is easy now that we know that P hat is equal to 0.43 and our margin of error E is equal to 0.0251363. We simply substitute those values in to obtain the result of P hat minus the margin of error is less than the population proportion is less than P hat, or sample proportion, plus the margin of error. So that gives us 0.43 minus 0.0251636 is less than the population proportion P is less than 0.43 plus 0.0251636. Or we can say that 0.405 is less than our population proportion is less than 0.455. So based on our evidence provided by our sample and the confidence interval obtained above, it does appear that fewer than 50% of adults have a Facebook page, because the interval of the values from 0.05 to 0.455 is an interval that contains, or excuse me, that is below 0.50. Another way of saying this is that we are, with 95% confidence, the percent of adults with a Facebook page is between 40.5% and 45.5%. If we were a reporter and we wanted to summarize the results of this sample, we might say that 43% of adults have Facebook pages. That percentage is based on a Gallup poll of 1,487 randomly selected adults in the United States. In theory, in about 95% of such polls, the percentage should differ by no more than 2.5 percentage points in either direction from our sample proportion of 43%. When analyzing results from polls, consider the following. First, the sample should be a simple random sample and not another inappropriate sample. Second, confidence levels should be provided. Third, sample size should be provided. And fourth, except for relatively rare cases, the quality of the poll results depends on the sampling method and the size of the sample. But the size of the population is not usually a factor. One note of caution: never assume that poll results are unreliable, even if the sample size is a small percentage of the population size. The population size is never really a factor in determining the reliability of a poll. In a situation where you are given just the confidence interval, you can calculate the point estimate of P using just that information. In that case, P hat would equal to the upper confidence interval limit plus the lower confidence interval limit divided by 2. And the margin of error would equal to the upper confidence interval limit minus the lower confidence interval limit divided by 2. Let's consider this example. The article High-Dose Nicotine Patch Therapy by the authors Dale, Hurt, et al. Include this statement. Of our 71 subjects, 70% were abstinent from smoking at least 8 weeks, with a confidence interval of 58% to 81%. Use that statement to find the point estimate P hat and the margin of error E. We can get our 95% confidence interval of 0.85 less than P less than 0.81 from the statement of 58% to 81%. So the point estimate P hat is the value midway between the upper and lower confidence interval limits. So we get P hat equals to 0.81 plus 0.58 divided by 2, and that equals to 0.695. And our margin of error can be found as the upper confidence interval limit minus the lower confidence interval limit divided by 2, and that is equal to 0.81 minus 0.58 divided by 2, which is equal to 0.115. A confidence interval can be used to informally address some claims made about a population proportion. However, if we plan to collect sample data in order to estimate some population proportion, how do we know how large our sample size must be? Our objective now will be to determine the sample size required to estimate a population proportion. Recall our notation is P equals our population proportion, P hat is equal to our sample proportion, N equals to the number of our sample values, E equals to our margin of error, and Z to the alpha over 2 is our critical value, the z-score separating the area of alpha over 2 in the right tail of the standard normal distribution. The sample must be a simple random sample of independent sample units. When an estimate P hat is known, then the formula for calculating our sample size is N is equal to the square of our critical value multiplied by P hat times Q hat divided by our margin of error squared. When no estimate of P hat is known, then the formula for calculating our sample size is N is equal to the square of our critical value multiplied by 0.25 divided by our margin of error squared. If the computed sample size N is not a whole number, then round the value of N up to the next larger whole number. So the sample size is sufficient instead of being slightly insufficient. For example, if the sample size is calculated to be 1067.11, then we would round it up to 1068. When the author of this textbook was conducting research for this chapter, he could find no information about the percentage of adults who make online purchases. Yet that information is extremely important to online stores as well as to brick-and-mortar stores. If the author were to conduct his own survey, how many adults must be surveyed in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points? First, assume that the recent poll showed that 80% of adults make online purchases. And second, assume that we have no prior information suggesting a possible value of the population proportion. With a 95% confidence level, we have alpha equal to 0.05. So our critical value of z to the alpha over 2 is equal to 1.96. Also, the margin of error is equal to 0.03. The prior survey suggests that p hat equals to 0.8. So q hat is equal to 0.2. We found this from the formula q hat equals to 1 minus p hat. Because we have an estimated value of p hat, we can use the formula n equals to our critical value squared multiplied by p hat times q hat divided by our margin of error squared. And so that gives us 1.96 squared multiplied by 0.2 times 0.2 divided by 0.03 squared. And that gives us a value of 682.951, and rounding up gives us a value of 683. So we would want to obtain a simple random sample that includes at least 683 adults. If we have no prior knowledge of p hat, or for that matter q hat, we would use the formula n equals to our critical value squared multiplied by 0.25 divided by our margin of error squared. In this case, that gives us 1067.11, rounding up to 1068. So we would want to obtain a simple random sample that includes at least 1068 adults. Our results can be interpreted as follows. To be 95% confident that our sample percentage is within 3 percentage points of the true percentage of all adults, we should obtain a simple random sample of 1068 adults, assuming no prior knowledge of our point estimate p hat. By comparing this result to the sample size of 683 found in Part A, we can see that if we have no knowledge of a prior study, a larger sample is required to achieve the same results as when the value of p hat can be estimated. So far, we've been learning what is known as the walled confidence interval for proportion. The walled confidence interval for proportion is p hat plus or minus our critical value multiplied by our standard deviation of the sample, where p hat is equal to the number of successes divided by the sample size. Now let's consider the +4 method of confidence intervals. The +4 confidence interval performs better than the walled confidence interval in the sense that its coverage probability is closer to the confidence level that is used. The +4 confidence interval uses this very simple procedure. Add 2 to the number of successes x, add 2 to the number of failures, so that the number of trials n is now increased by 4, and then find the walled confidence interval as previously described in this section. So now our +4 confidence interval is equal to p hat plus or minus our critical value multiplied by the square root of p hat times q hat divided by n, where p hat equals to the count of successes plus 2, the count of the sample plus 4, is equal to x plus 2 over n plus 4. There are other methods for constructing confidence intervals that are not discussed here. However, there isn't any universal agreement on which method is best for constructing confidence intervals to estimate our population proportion of P. However, the walled confidence interval is the best tool for teaching students in an introduction statistics course. And the +4 confidence interval is almost as easy as the walled, and it performs better than the walled by having a coverage probability that is closer to the selected confidence level. That's everything for Chapter 7, Section 1. Next week, we will start learning about confidence intervals for population means.